So in this video, we're going to be talking about what happens when you make an aqueous solution of an acid or a base. All right. You've probably heard before that a certain substance is either acidic or basic. All right. For example, might have heard that vinegar is acidic, or you might have heard that soapy water is basic. All right. But literally, what does that mean? All right, so before getting in, you might just think, all right, well, it means that if it's acidic, it contains an acid, or if it's basic, it contains a base. And to some extent, that is true, but the exact definition actually has to do with something a little bit different, all right? So before getting into the definition, we need to start with a little bit about the behavior of water, all right? And if I were to give you the purest water on Earth and say, what is this substance? All right. Or what does it contain? You would probably say it contains H2O. All right. And for the most part, that's correct. But even the purest water on Earth is not 100% H2O. All right. And that's because of a peculiar behavior that water has. All right. Water undergoes what's called the self-ionization of water reaction. All right. And essentially, this is what happens when every once in a while, one water molecule temporarily borrows an H plus from its neighbor. All right, it's kind of like one water molecule says to the other, "Hey, could I borrow one of your H pluses?" All right. So let's pretend that this water molecule is right next to this water neighbor. All right, and this thing, so this electron pair is capable of picking up an H plus, all right, and the electron pair that's in this bond right here is capable of going back onto that oxygen, all right. So this water molecule, if it temporarily gained that, accepted that H plus, would become H3O plus, and this water molecule, when it temporarily lost that H plus, would become hydroxide, all right. So the thing about this reaction is that it's reversible, all right. So almost as soon as this one accepts an H plus from this molecule right here, it almost immediately gives it back. All right, and so before talking about some of these behaviors, just note that this particular reaction right here, I've drawn it as Lewis structures, but it could be represented like this, where you represent it as formulas. All right, where you have two water molecules right here, that's the two H2Os, and it makes a single hydronium ion, that's this guy, and this hydroxide ion right here. All right, so again, a couple things about this reaction. First of all is that it happens very infrequently, all right? So even though it does happen some, all right, if you've got a sample of water, well over 99.999% of the molecules are just going to be plain old water molecules. All right, but this only happens to a very, very small number of molecules at any given point in time. All right, so to be exact, at any point in time, that reaction that I just showed is only happening to about 2 out of every 555 million water molecules. All right, so we're going to talk about that a little bit statistically in just a second. All right. The other thing about this is, even though it, in addition to it happening very infrequently, it's almost immediately reversible. All right. So this hydronium ion does not hold on to that H plus for very long. It either gives it back to the hydroxide or it transfers it to another neighboring water molecule. But it does not exist. These species do not exist for very long. All right. So how does this have, what are these two things? How would they affect water? All right. Well, the thing is, it seems like it happens so infrequently that it wouldn't have much of an effect. But let's think about what happens in a cup of water. All right. If you've got a cup of water, all right, that single cup of water contains about this many water molecules. All right. It's an overwhelmingly large number. All right, that's 20 with, I want to say 24 zeros after it. All right, sorry, 2 with 24 zeros after it. All right, so I can't even say the number that's that large. In fact, we would normally represent it with scientific notation. All right, but what we said was, statistically, about 2 out of 555 million molecules would be undergoing that reaction. All right. Well, that almost seems like it never happens. All right, if it's only happening to this much, but I've lined these numbers up. All right, that is the these zeros right here are the same amount of digits as this. There are way, way, way more water molecules in that cup of water than just this right here. All right, so even if this is only happening to about 2 out of 555 million, all right, there are so many water molecules in that cup that you know that this is actually going on a ton. All right, and this is one of the things about statistics. Even occurrences that happen very rarely, if you have a large enough population, it's almost it's almost guaranteed to happen. All right, so even a rare occurrence, like most of us, it's fairly rare for us to get into a car accident. All right, but we know that, like, with a population that's as large as ours is in the United States, there's almost guaranteed to be at least one car accident every day. All right, and in fact, I'm sure that at least somewhere in this country, there's a car accident every day, even though for an individual, that is a very rare occurrence. All right, so same thing goes on here. So what this means is that in that cup of water, there is still plenty of H3O plus and OH minus, even though over 99.9% of the molecules in this are H2O, you still have a statistical amount of this in that water. All right, so this paragraph right here just kind of sums up what I just showed in that graphic right there, just demonstrating that, like, in that water, you're going to have some of those chemical species. All right, so the way that we actually describe the amount of these that are in the water is by using their molar concentrations, or as we described in solutions, their molarity. All right, and that's why I put these square brackets around the chemical formulas. All right, so that means this right here means the molarity of the hydronium ion dissolved in the water, and this would mean the molarity of the hydroxide ion dissolved in the water. All right, so what happens is that if you have pure water, all right, notice in this reaction that we showed before, the same reaction that generates one hydronium ion would produce one hydroxide ion. So in pure water, that's what you're going to have. You're going to have the same number, the concentration or the molarity of H3O plus is going to equal the OH minus. All right, and the other thing about this, and we're not going to get into why this is, that it's known that in all water, whether it's pure or impure, all right, the molarity of H3O plus times the molarity of hydroxide ion equals 10 to the minus 14th. All right, so we could represent that by doing this, just saying these are the two molarities multiplied by each other, and those always are going to equal 10 to the minus 14th. All right, and that relationship is called the ionization constant for water. All right, so what this means, what does this little mathematical relationship mean? All right, well, let's just give an example. If I said that A times B equals 100, all right, well, what would happen if A goes up? If A, like, let's just say 10 times 10. All right, well, what happens if A becomes 11? Well, in order for this still to be true, B's got to go down. When you have one number times another number always equal to a constant, if one of them goes up, the other one has to go down. All right, and because of that, one way to think about this is that you have this seesaw relationship between the amount of H3O plus and the amount of OH minus. All right, because when they're multiplied by each other, they always have to equal the same number. All right, so this is essentially what makes water either acidic, basic, or neutral. All right, and it all has to do with the relative amounts of H3O plus and OH minus. All right, so let's start off with pure water as an example. If you have pure water, what I'm representing with the seesaw is that you would have equal amounts of both of these in the water. All right, so let's pretend that you were to add a little bit of weak acid to that water. All right, something like, a little bit of vinegar. All right, what that's going to do is it's going to add a little bit more H3O plus than OH minus. And so that's going to tip the scale a little bit more towards the H3O plus. This is showing a little bit more of this than of this. All right. But what if we then added a strong acid to that? All right, well, that's going to tip it majorly in favor. All right, so this is something we would describe as weakly acidic, and this would be extremely acidic. All right, so this might be something that's weakly acidic would be something like, vinegar or lemon juice. All right, things that are strongly acidic or extremely acidic, battery acid. All right, hydrochloric acid. All right, we're going to give some more examples of those later. All right, but what about like if you took pure water and you added a little bit of a weak base? All right, and we're going to talk about what it means to be a weak base versus a weak acid in just a second. Well, what that's going to do is it's going to, instead of these things being level, it's going to tip it a little bit towards the hydroxide. So once you add that weak base, you're in that solution that you make, you're going to have a little bit more hydroxide than you do H3O plus. Right, and that's going to make that solution slightly basic. All right, so a good example of that would be soapy water. All right, so let's pretend that we then added a strong base to that. All right, something like sodium hydroxide. All right, that's going to tip the scale way towards the OH minus. But notice if you add OH minus, the amount of H3O plus has got to go in the opposite direction. So solutions that have lots of OH minus have very little H3O plus, and solutions that have a lot of H3O plus have very little OH minus, all right, because that relationship between one of them times the other has always got to equal this number, and that creates the seesaw relationship. All right, and because we have this seesaw relationship between these amounts, and that's what actually makes it either acidic or basic. Well, we would want to be able to describe, well, how much tipped in, first of all, which direction is it tipped towards? And second of all, how much is it tipped? All right. And so one way, I can represent it graphically by showing these seesaws, but another way would be to try to quantify this so that we had a number. All right. And the way that we do that is with what's called the pH scale. And hopefully you've heard, I'm assuming that you've heard of pH. All right, so we're going to get into exactly what is meant by pH in the next video.